Hello, I'm Tim Fox, and I'll be discussing Arbiter-PUF faults, impact, testing, and diagnosis. This paper was written by Yechi Wei, myself, Vincent Dumoulin, Wenjing Rao, and Natasha DeVroy. We're from the Department of Electrical and Computer Engineering at the University of Illinois, Chicago. First, I will talk about the general model of physically unclonable functions, known as PUFs, as well as their metrics. Then I will discuss arbiter PUFs, their fault models, and our test and diagnosis methodology. I'll conclude with results from the simulations of our methods. PUFs are hardware security primitives which act as a unique fingerprint to identify and authenticate chips, such as those found inside of Internet of Things devices. Ideally, PUFs should be designed to be identical, but manufactured to be unique, unclonable, and inexpensive. As a function, a PUF takes an n-bit binary sequence, or a challenge, as input, and outputs a binary response. Each challenge and its response forms a challenge-response pair. A strong PUF offers a truth table exponential in the size of its hardware cost. By mapping n inputs to 2 to the n outputs, a strong PUF prevents the enumeration of every challenge-response pair. This property helps to ensure that the PUF is unclonable. The response bias of a PUF is the ratio of positive responses in its truth table. An ideal PUF has a response bias of 50%, or an equal chance for either response. We can consider some 3-bit PUFs to demonstrate this metric over the 8 possible challenge response pairs. PUF number 1 has 1, 2, 3, 4 positive responses to the 8 challenges, and so its response bias is 4 out of 8 or 50%, and it's unbiased. PUF number 2 has 3 out of 8 positive responses, therefore it has a response bias less than 50%. In other words, it's biased to have more negative responses than positive. On the other hand, PUF number 3 has 5 out of 8 positive responses, so it has a response bias greater than 50%. An important question to consider for the manufacturing of good PUFs is what type of faults might cause their response bias to deviate far from 50%. Such a fault would make a PUF's responses easier to guess, which reduces its security. PUF uniqueness is the ratio of different responses between a pair of PUFs' truth tables. An ideal set of PUFs has an average pair uniqueness of 50%. Or having a different response from each other half of the time. Considering the same 3-bit PUFs from before, we can see that PUFs number 1 versus number 4 only differ in 2 out of 8 or 25% of their responses. This means they are too similar to each other and not unique. PUFs number 2 versus number 4 differ in 5 out of 8 of their responses, or 62.5% of the time. These PUFs are very unique relative to each other, but this is not a property that can hold across a large batch of PUFs, since a challenge has only 2 possible responses. PUFs number 3 versus number 4 differ in 3 out of 8 of their responses, or 37.5% of the time. Another important question a PUF manufacturer should consider is the type of faults that might cause the uniqueness of a batch of PUFs to deviate far from 50%. Such a fault would make these PUFs less useful for authentication, as their fingerprints are too similar to distinguish between chips. An arbiter-based PUF, or APUF, is an implementation of a strong PUF where each response depends on the delay difference between 2 racing paths, which are configured differently for each challenge. 2 APUF models are shown here: a detailed multiplexer implementation and its abstract representation. I'll explain how an APUF operates for a single challenge response pair. Each stage of an APUF is issued a challenge bit to configure the multiplexers, selecting a unique set of delays. A pulse is issued to the input of the first stage, where it branches off into 2 racing paths. Since the first stage's challenge bit is 0, the parallel tracks called T and U are selected. Since the second stage's challenge bit is 1, the crossing tracks called R and S are selected. Next, at stage 3, the parallel tracks T and U are selected again. In either case, the yellow and blue racing paths always take separate tracks in order to accumulate their separate delays. After the final stage of an APUF, a D flip-flop serves as an arbiter that detects which of the two racing signals wins the race. The response to the challenge is determined by the arbiter. If the pulse arrives at the top port first, the response is positive. Otherwise, when it reaches the bottom port first, the response is negative. This response depends on the challenge as well as each stage's unique delays. In either of these two APUF representations, we can see that each stage has 4 selectable tracks for signals to flow. A stage's challenge bit selects either the parallel T and U or the crossing R and S tracks. Each of these track pairs are designed to be equal, having the same delay D. However, they each have a unique delay due to the random variance during manufacturing, and thus have an IID normal distribution with a mean delay D. Arbiter puffs can be analyzed mathematically in different ways. For a particular challenge, we define the accumulated delay difference between the upper and lower paths after any stage I as big delta I of C. For example, delta 3 of C would be the accumulated difference in delay between the blue and yellow paths after stage 3. After the final stage N, which is 4 here, we have the final accumulated delay difference, delta N. The response to any challenge is simply the sign of this final difference in delay. When the pulse reaches the top port of the arbiter first, both the delay difference and the response are positive. Otherwise, when the pulse reaches the bottom port of the arbiter first, both the delay difference and the response are negative. We can simplify this model further by noticing that at each stage, either the T and U or R and S track pairs are always selected together. This allows us to define delay difference elements, or deltas, which are named after the challenge bit that selects them. Small delta 0 at stage I is for the parallel tracks, and small delta 1 at stage I is for the crossing tracks. These represent the possible choices of delay differences to be accumulated at each stage I. As the difference of two IID normal random variables with a mean delay D, these deltas have a mean delay of 0. Now that we have per stage deltas to simplify the model, we can use a simple recursive formula to calculate the accumulated delay difference delta I after any stage. If delta 0 is chosen, the parallel tracks are taken and the delay difference delta 0 is added to the running total from the previous stage. If delta 1 is chosen, the crossing tracks are taken. The signals swap between the upper and lower positions and the running total from the previous stage is negated, after which the delay difference delta 1 is added. In the end, we have a final accumulated delay difference delta N, and the response is the sign of this difference. Although the final accumulated delay difference delta N is not measurable in a real physical APUF, one can simulate APUFs and view a histogram of the delta N values over a random challenge set to get a sense of the response bias. A good APUF having all delay elements about 0 has a normal delta N distribution and has a response bias around 50%. If we consider some bad APUFs, where small delta 0 at stage 30 has an abnormal value deviating far from 0, we notice an effect on the distribution of their delta N values. As this abnormal value increases in magnitude, we start to see multiple humps form in the histogram. Interestingly, each of these bad APUFs is still unbiased with a 50% chance of either response. However, one needs to carefully establish fault models and examine their impact on a batch of APUFs' response bias and uniqueness. To investigate the effects of a bad APUF production, we first considered 2 fault models that deviate from the assumption of good APUF production where the deltas at all stages follow an IID normal distribution with a mean of 0. One possible fault that could arise is a mu fault, which deviates from the assumption that all deltas are of 0 mean. This could be caused by an unbalanced placement and routing in the design phase, causing all the manufactured APUFs to have a particular abnormal delta with a non-zero mean. Another possible fault is a sigma fault, where a flaw in the production process results in increased process variation, also causing an abnormally large delay difference. The next question to ask is, what are the impacts of these faults? We've already shown that abnormal deltas usually do not affect the response bias of an APUF. These plots of the response biases of single bad APUFs, each having a single mu or sigma fault, confirm that across a wide range of fault intensities K, the response bias is not impacted as long as the fault does not occur at the final stage. However, it's important to note that both mu and sigma faults can have a major impact on the response bias if they do occur at the final stage in. Manufacturers must ensure that there is a much lower tolerance for error at the final stage, both in the design and in the process variation. Next, we will look at similar data for uniqueness, the probability of a difference in response to some challenge across a batch of puffs. In these plots, each point is the uniqueness calculated between a pair of bad APUFs from the same faulty manufacturing process. We see a significant impact on uniqueness for both mu and sigma faults at any stage, and the effect increases as an abnormal delta's magnitude increases. Therefore, it's important that manufacturers maintain strict control over both the design and the process variation across all stages, otherwise there can be a strong impact on APUF uniqueness. Mu faults in particular have the potential for devastating effect on uniqueness, which is seen as the magnitude of the fault intensity K increases. For this reason, we also considered how multiple mu faults might affect uniqueness. The data in blue is similar to what was shown in the previous slide with single faults, but here we are averaging the uniqueness of 1000 APUFs and only considering the positive values of K. With a single mu fault, there is a 50% chance that a challenge will not select the abnormal delta, decreasing uniqueness to 25% as K grows large. Intuitively, more faults result in lower overall uniqueness. This is verified by the orange line, where two mu faults occur at different stages common to the entire batch of APUFs. The chance of avoiding an abnormal delta drops to only 25%, so we see a slightly stronger impact to the uniqueness. Alarmingly, when the two mu faults occur at the same stage, their impact can drive uniqueness all the way to 0% because a challenge will have to select one of the two abnormal deltas. When every single delta has a mu fault, we see a sharp drop in uniqueness, even at low fault intensity. In this case, each puff in the batch has nearly identical non-zero delay differences at each stage, and will respond the same to most challenges. This concludes the impacts of production faults on APUFs. The more deviation from the good puff standard, where all the deltas are of zero mean with a common variance, the worse the performance of the APUFs, particularly in their uniqueness. When testing an individual bad APUF, rather than a batch coming off the same production line, one will not be able to tell if an abnormal delta is the result of a mu or sigma fault. Thus, it's important to define a more generic delta fault model for individual APUF instances, in which a delta is considered abnormal if its magnitude exceeds some threshold T. This threshold can be chosen based on the fault intensity K and process variation sigma deemed acceptable by a manufacturer. Using the delta fault model, we will now present the main idea of testing and diagnosing such a fault. Challenges are controllable, responses are observable, but the individual delta delay elements and accumulated delta in delay differences are invisible in a real physical APUF. A good APUF has a response bias of 50%, but as we've shown before, most bad APUFs also have a response bias of 50%. This presents a problem. We cannot tell a good and bad APUF apart with a random challenge set. In order to determine the best challenge set to test for bad APUFs, we need to delve deeper into how a challenge selects each delta and its sign. One of two delay differences is chosen at each stage, either delta 0 or delta 1 if the stage's challenge bit is 0 or 1 respectively. The chosen delta is included in the final accumulated delay delta in. However, this chosen delta could be included in either positive or negative form in the final delta in. How is this sign determined? Since a chosen delta's sign is flipped each time the crossing tracks are selected afterwards, the sign of a delta included in the delta in depends on the parity of the challenge bits issued to the remaining stages. If there is an even number of ones, then the two racing signals will swap paths an even number of times, preserving the sign of the delta chosen at the current stage. Otherwise, the signals swap paths an odd number of times and the sign of the chosen delta is flipped. One special case is that the delta chosen at the final stage in has no remaining stages that could flip its sign, and therefore it is always chosen in positive form. We can use these insights to derive special challenge sets that provide us with a method to test for bad APUFs. We call these target sets because each set's challenges target a particular delta at a particular stage being included with a particular sign in the accumulated delta in. They are formed by partitioning a random challenge set into 4 disjoint subsets for each stage. Here is an example showing how to derive target sets for the second stage of a 4-bit PUF. First, we divide the challenges based on the delta they are selecting at the target stage. Then, for each challenge, we check the parity of the challenge bits from the next stage until the end. These first 2 challenges selecting delta 0 at stage 2 have even parity for their last 2 bits, so they're a part of the challenge set selecting delta 0 at stage 2 in positive form. The next 2 challenges selecting the same delta have odd parity for their last 2 bits, so they're part of the set choosing delta 0 at stage 2 in negative form. The same logic applies to the challenges selecting delta 1 at stage 2, which leaves us with 4 target challenge sets from 1 random challenge set. These target sets allow us to better perceive the biases within an APUF. In the histograms of delta in for bad APUFs shown previously, the side humps are formed exactly by the target sets selecting the abnormal delta. The middle hump is formed by the target sets not selecting the abnormal delta. Now that we've partitioned these challenges from the original set for each stage, we can use the response biases of the APUF on each set to determine if a particular delta at a particular stage is imparting a strong bias due to an abnormal delay difference. If the target sets of a delta have response biases deviating far from 50%, then it's an abnormal delta, a delay difference too far from 0 in either the positive or negative direction. If the response bias on the positive target set is much larger than 50% and the response bias on the negative target set is much lower than 50%, then this delta is abnormally positive. We use the difference between these pairs of response biases to help diagnose these abnormal deltas. In algorithmic form, the process works as follows. On the first iteration I equals 1, we split a random challenge set into the target sets for delta 0 at stage 1 and delta 1 at stage 1. We collect the APUF's response biases for each of these 4 sets and then compute the difference between the biases for each delta, which we call the difference scores. The abnormal delta threshold T, as well as the tolerances for false positives and false negatives, are specified by the manufacturer. These specifications then translate to the difference score threshold gamma. We will discuss this more later. Once we have the difference scores for both deltas at stage I equals 1, we compare their values to the chosen gamma. If a delta's difference score is larger than gamma, then it's larger than a threshold T and is abnormally positive. If the difference score is smaller than negative gamma, then it's smaller than negative T and that delta is abnormally negative. Once the first stage has been tested, we repeat this process for stage I equal to 2. The main change is that new target sets targeting the deltas at stage 2 are formed from the random challenge set. We then perform the rest of the calculations again using the new target sets. The process repeats again for stage I equal to 3. Once we reach the final stage I equal to n, which is 4 here, there is a special case to consider compared to the previous iterations of the algorithm. Since the delta chosen at the last stage of an APUF is always chosen in positive form with no possibility to be flipped, the target sets that select either of the deltas at stage N in negative form are empty sets. For an empty target set, we assign the default value of 0.5 as its response bias. We then double the difference score of stage N to normalize it to the same range as the other stages. These plots show how this algorithm helps us to perceive abnormalities in the invisible deltas. Since this is from a simulation, the first row shows the true value of each delta in this APUF. It has two abnormal deltas. Delta 0 at stage 10 has a fault intensity K equal to negative 10, and delta 1 at stage 50 has a fault intensity K equal to positive 10. The second row shows all of the response biases calculated using the target sets at each stage. A large increase in bias can be seen at stages 10 and 50 where the faults are located. The third row shows the difference score of each pair of biases at each stage. The strong biases result in a strong bias difference, which we use for our diagnosis. As stated previously, our difference score diagnosis threshold gamma is chosen based on tolerances set by the manufacturer. In this example, we can notice that gamma equal to 0.5 would allow us to diagnose the two abnormal deltas while avoiding the misdiagnosis of any of the surrounding deltas. As we will show soon, the choice of gamma changes the trade-off between true and false positive rates of abnormal delta diagnosis. Our primary simulations used to verify the proposed testing and diagnosis algorithm were performed over 1064-bit bad APUFs. We used a variable number of delta faults and fault intensities K. These results are for bad APUFs being correctly identified as bad, but not necessarily pinpointing the exact abnormal deltas. The simulations show that once K is greater than 10, our methods have a detection rate of nearly 100% for up to 4 abnormal deltas in each of the bad APUFs. The next simulation results are for the correct diagnosis of the exact abnormal delta position and sign. The setting is the same. While the number of exactly diagnosable abnormal deltas drops to about 2 per bad APUF, these have a diagnosis rate near 100% once K is greater than 10. This receiver operating characteristic or ROC curve shows the trade-off between true and false positive rates of abnormal delta diagnosis. Ideally, we want a false positive rate of 0% and a true positive rate of 100%, but we can only come close to this once the fault intensity K is high enough. The trade-off depends on the difference score diagnosis threshold gamma, which itself depends on the abnormal delta tolerance threshold T equal to K sigma chosen by the manufacturer. These parameters must be considered carefully. The value of T chosen depends on the minimum desired APUF uniqueness. Then gamma can be adjusted based on the maximum tolerable false positive rate, or the percentage of good chips being thrown away. We nearly reached the ideal true and false positive rates for K equal to 10 and gamma equal to 0.4. With lower fault intensities like K equal to 2.5 or 5, the value of gamma must be lowered in order to reach acceptable true positive rates. To conclude, we have presented new statistical fault models which are native to Arbiter-PUFs. In batch APUF production, there are mu faults and sigma faults resulting from either the design mask or the manufacturing process variation deviating from APUF standards. For individual APUFs, there is the more generic delta fault in which a delta's value exceeds a threshold due to mu or sigma faults in batch production. We showed the impacts that these faults can have on the common PUF metrics of response bias and uniqueness, and we determined that these faults will in fact result in less usable Arbiter PUFs. We proposed an algorithm that can be used for the detection of bad APUF instances as well as the diagnosis of abnormal delta elements. Our simulations showed that this algorithm has a high rate of success with a reasonable fault count. This concludes my presentation, and I thank you for listening.